Yesterday, we started with some notes. I'm hoping to finish those today if we have time. We'll see. We talked yesterday about the gravitational field qualitatively as the region of space around a mass. For another point, mass experiences force. I know I put that in definitions. Covered. Done. Diagram the Earth's gravitational field using lines of force. Remember this?
Yeah.
We talked about that. Done. Define the gravitational field quantitatively as a force per unit mass. I know I did that because I meant for saying, I brought out the 1 kilogram thing and I said it's 9.8
I still haven't copied down that last page notes.
newtons per kilogram.
A lot of work.
I haven't talked about mass and weight yet. Oh, no, I did do that a little bit.
Ace isn't here for any of it though, so you can't put a check mark.
This, you can watch the video. This we'll talk about later. Today we're going to talk about free fall. And before we can solve free fall problems, we need to talk about free fall. So, free fall explained. Pisa, Galileo's famous demonstration, which Jake basically reproduced for us yesterday, right? Galileo showed that falling objects accelerate equally regardless of their masses. This is strictly true if air resistance is negligible, that is if the objects are in free fall. It is approximately true when air resistance is very small compared with the mass of the falling object. For example, a 10 kilogram cannonball and a 1 kilogram stone dropped from an elevated position at the same time will fall together and strike the ground at practically the same time. This experiment, said to be done by Galileo from the Leaning Tower of Pisa, demolished the Aristotelian idea that an object that weighs 10 times as much as another should fall 10 times faster than the lighter object. Galileo's experiment and many others that showed the same result were convincing, but Galileo couldn't say why the accelerations were equal. The explanation is a straightforward application of Newton's second law and is the topic of the cartoon Backyard Physics. Let's treat it separately here.
What happens if you drop a feather and you drop a 10-pound weight?
Okay, good question. 10-pound weight, feather. Why will the feather sort of go like that? Because air resistance is not negligible. If Jake had gone 6 miles up and dropped the milk, was it a milk jug?
Yeah.
Milk jug and the 1 liter, right? Would they fall at the same rate then?
No.
It might be noticeable, right? The bigger one has a bigger surface area, much like a piece of paper, but it's heavy, right? So it can sort of plow through the air a little bit more. If you were to drop, say, like a penny and a 10 or a 4-liter jug of water, which one would probably be more susceptible to air resistance? The penny, right? It's just it's light and it's reasonably flat.
Can't feel 1 kg.
No, not necessarily.
Yeah, but it's not gonna like float in the air like this. It's gonna.
Oh, okay. Now, good question. When you say float, do you mean like suspend, or do you mean like sort of flutter down?
It's gonna go straight up and down. It's cut through the air.
It might do that, yeah.
It's not
Yeah.
gonna like. It's not like you know, a piece of paper where it's gonna go like that.
You know the myth about throwing the pennies off the Empire State Building? Can't do it because you might kill someone? Busted. Air resist. The terminal velocity is so low that you throw the penny off the Empire State Building, and it really. What they did, I can show you the video. The Mythbusters, they created. Yeah, I'll show it to you. They created. They took a staple gun and they modified it to shoot pennies. And because they figured out how fast they would actually go as they reached terminal velocity. He jumped out of a plane, threw some pennies, figured out how fast they were falling, modified the staple gun so it would shoot that fast, and then he shot it in his hand. It didn't even make a mark. It hurt, but it didn't make a mark, so it wouldn't kill anyone. It's a myth.
And one where they made like the ping pong balls go like right through a paddle.
I didn't see that.
It was cool.
Okay, let's keep going. Recall that mass, a quantity of matter, and weight, the force due to gravity, are proportional. A 2 kilogram bag of nails weighs twice as much as a 1 kilogram bag of nails. So a 10 kilogram cannonball experiences 10 times as much gravitational force. That is true. Okay, and you guys might want to highlight that. 10 kilograms. The amount of force on 10 kilograms is considerably more than 1 kilogram, the gravitational force, right? So how come that 10 kilogram mass doesn't accelerate faster? But we know the weight force, right? It's 9.8. The weight force here, oh man, can't write. The weight force here is 10 times 9.8, or 98 newtons. Over here, it's 1 times 9.8. 9.8. The force is 10 times bigger. How come it doesn't go 10 times faster? Because there's one more thing that's 10 times bigger. I've already told you what it is. Nope. Mass. And isn't it m times a? Right? So if the force gets 10 times bigger, well, that's because the mass is 10 times bigger, leaving the a exactly the same. That's what it says right here. The followers of Aristotle believed that the cannonball should accelerate at a rate 10 times that of the stone because they considered only the cannonball's 10 times greater weight. However, Newton's second law tells us to consider the mass as well. Although thought will show you that 10 times as much force acting on 10 times as much mass produces the same acceleration as the smaller force acting on the smaller mass. And there it is in symbolic notation, almost exactly the same way as I've got it there. Big F over big M, right? Like if this is 98 and that's 10, well, that's the same thing as 9.8 over 1, which is gravity. Okay? Now, it's hard to believe. I really honestly find this hard to believe that Aristotle taught people that, and for 2,000 years they said, oh yeah, okay, that's right. No one ever actually took out a bigger cannonball and a smaller one and kind of looked around, no one looking, okay, cool, do that at the same time. Like, no one did that. That's hard to believe. Certainly he must have been some sort of, wizard or something. He had, like, brain power over people, or he was a really scary dude and no one wanted to mess up with him. Yeah, I don't know. Okay. Blah, 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 blah. Right? So we got 9.8 meters per second squared. Acceleration of the cannonball, 9.8 meters per second squared feet. In the famous coin and feather in a vacuum tube demonstration discussed in Chapter 2, the reason for the equal acceleration was not discussed. Now we know that both freely falling objects fall with the same acceleration, because the net force on each object is only its weight, and the ratio of weight to mass is the same for both. So my question to you is, is that my question to you? There it is there. I'll start this, and while you answer that, I will click on the video, hopefully, and we will watch it. So if you were on the moon and dropped a hammer and a feather from the same height at the same time, would they strike the surface of the moon at the same instant? Because they sure wouldn't here on Earth, would they? Go. Would they hit the ground at the same time? Yes. I'm hoping you guys got that. Yes, they would. How come? Because there's no air resistance. Now, the only way to prove that is to actually go.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time.
Really, Lucas? You can't just, put it away for, 45 minutes?
Mr. Galileo was correct in his findings.
You missed it.
I saw him. Is that from when they first went?
This was not the first landing on the moon. This was astronaut David Scott, so it would have been about 1971 or so. Why did he say appropriately a falcon feather, do you think?
Because it's like big feather.
I think the landing ship was the Eagle, was it not? Falcon?
Ironic.
I think so. Yeah, it wasn't ironic, but yeah, so absolutely true. Galileo was right. Okay. What if, now do you guys have this question?
No.
Look, I got cut off. But you got them all wrong. Oh, there's probably the two. Okay, so let's do this one. How many are there? There's three? Okay, well, let's do them. Oh, I know why. Because these two are on the back side. Okay, we'll come back to that one. Let's flip and look at the cartoon one there on the back here. Backyard physics. if I drop the bag of clothespins, not because every mom does this out the window, right? Heather, you need to put it away, seriously, or it's going like away. You gotta pay attention. If I drop the bag of clothespins and the single pin at the same time, which will hit the ground first? So the one kid says that's easy. The bag of clothespins is heavier, which means gravity pulls on it with more force. Is that true?
No.
Actually, it is true.
That is true.
I don't think that-
So the bag of pins will accelerate more and hit the ground first. The other kid scratches his head and says physics. Not true. The bag of clothespins has more mass, which is to say it has more inertia. It will be less responsive to gravity and lag behind the single pin.
People talk like this.
No one talks like that. Is that true though? Yes, it does have more mass, which is to say it has more inertia. That's true as well, right? So he says the single pin will hit the ground first.
Sorry.
But when he lands, when the woman drops them, what happens? They land at the same time. Because both of those things are true, right? As we said in the previous page, big weight over big mass is the same ratio as little weight over little mass, and the gravity, the acceleration is the same.
What about big mass and big acceleration?
Well, if you had big mass, right? Can you have big mass without big weight?
Yeah.
No, because everywhere on Earth, what's the acceleration due to gravity? It's 9.8. You can't go anywhere. I mean, you can go top of Mount Everest, I guess, but it's not going to change that much, right? There's no way you can change that ratio. Weight is dependent upon mass. That's just the way it works.
It's really small, but really heavy.
Someone's really dense.
Okay, let's talk about falling and air resistance. I got a couple demonstrations here as well to show you. Backside here, Nate. Second sheet. Falling and air resistance. The feather of the coin, or the falcon feather and the hammer on the moon, fall with equal acceleration in the vacuum, but quite unequally in the presence of air. When air is let into the glass tube and is again inverted and held upright, the coin falls quickly while the feather flutters to the bottom, just like a piece of paper, right? Air resistance diminishes the net force acting on the object. The net force decreases a tiny bit for the coin and the lot for the feather. The downward acceleration for the feather is very brief because the air resistance builds up quickly and counteracts its tiny weight. The feather does not have to fall very long or very fast for this to happen. When the air resistance on the feather equals the weight of the feather, the net force is zero and no further acceleration occurs. Do you remember the fat cat in the pool question
No. Yes.
that you all argued with me about?
We argued.
Oh yeah, lots of you did. Okay, so here's the feather. All right, I'm not a very good drawer. Yeah, it does look like a leaf. Same idea, I guess, right? This is the weight force, right? Air resistance is kind of funny. As you go faster and faster, the air resistance gets bigger and bigger and bigger. So when it just starts to fall, it's like that. Is it still accelerating? Yes, it is. But as you go faster and faster, this thing here gets bigger and bigger until eventually they are the same. Oh, that's just terrible.
That's like terminal velocity.
And at that point, correct, Lucas. At that point right there, let's just redraw it. At that point right there, when the air resistance is equal to the weight force, then the net force is zero, which means the acceleration is zero, which means you have reached terminal velocity. Which means you fall at a constant rate. Do you float? No, you just continue to fall at a constant rate. When you jump out of an airplane, you accelerate for a while, and then eventually what happens? You reach terminal velocity. What happens when you pull the parachute?
You go up.
Do you go up into the air?
Yeah.
Really?
First.
No.
Go up.
Yeah, it'll pull you up.
Really? Like you actually go up into the air?
Yeah, and then you go
You're
back down
in
again.
Google it.
Let's watch a video on how long that works. Let's watch
When you put your, you mean like when you
Like
first
when you
pull
pull
it,
a chute,
you
you
go up.
actually go up.
Yes, because it pulls you up.
Really?
You just slow down.
Still falling when that
You're
happens.
not-
Pulling the right
That's
way.
not floating. You're not floating. You're going like this, and then you get your parachute and you go slowly.
What they say. They're right. Here, the reason you think that is because
They stop.
when they show this, they always have what? They always got two people doing it, right? This guy's got a camera on his head, right? And when this guy pulls the parachute, what happens?
He goes out, and the other guy.
No, they both continue to fall, but this guy falls a whole lot faster. This guy still falls.
Have you jumped out of the plane?
No, I have not jumped out of the
Exactly.
plane.
Let's go ask this kid. She actually jumped.
I know, in Switzerland.
Yeah. Let's get over here. Let's get over here. Debate.
She's busy, I'll ask her. Yes, so you do not go up like that. It just looks like that. It's all based on your,
You gotta just
like, if you were down here on the ground,
What did you?
if you were down on your point of view, your frame of reference, if you're down on here on the ground, you still see the guy with the chute falling, just not as fast. This guy goes, psh,
This guy actually goes to.
yeah. Then he goes, ah, when he hits the ground. Okay. Where was I here? Terminal velocity. If we're concerned with direction, which is down for falling object, say the feather is reached, it's terminal velocity. Air resistance does not have as much effect on the coin. At slow speeds, the force of air resistance is very small compared with the weight of the coin, and its acceleration is only slightly less than the acceleration of free fall. The coin might have to fall for several seconds before its speed is great enough for air resistance to equal cancel its weight. At this point, perhaps as much as 200 kilometers an hour would no longer increase. The coin reaches its terminal speed. The terminal speed for a skydiver varies from about 150 to 200 kilometers an hour, depending on the weight and orientation of the body. A heavier person will attain a greater terminal speed than a lighter person. The greater weight is more effective in plowing through air. Right? Same reason why a bigger person will go down a toboggan hill at a faster speed. The greater weight is more effective in flying through the air. Body orientation makes a difference. More air is encountered when the body is spread out and the surface area is increased, like that of the flying squirrel in the picture there. Terminal speed can be controlled by variations in body orientation. You should be listening to me. Don't talk. You can't talk and listen. A heavy skydiver and a light skydiver can remain in close proximity to each other if the heavy person spreads out like a flying squirrel, while the light person falls head or feet first. Parachute greatly increases air resistance and cuts terminal speed down to 15 to 25 kilometers an hour, slow enough for a safe landing. If you hold a baseball and a tennis ball at arm's length and release them at the same time, you'll see them strike the floor at the same time. But if you drop them from the top of the building, you'll notice the heavier baseball strikes the ground first. This is due to the buildup of air resistance at higher speeds, like the parachutists in the question. At low speeds, air resistance is often negligible, but at high speeds, it can make quite a difference. The effect of air resistance is more pronounced on the lighter tennis ball than on the heavier baseball, so the acceleration of the fall is less for the tennis ball. If I went out to the golf course and I snuck a ping pong ball and made it look like a golf ball, and you hit it,
Probably break.
it would probably break. But you can have some. You know those plastic practice golf balls? How far can they go? They go a little ways, but not near as far as a regular golf ball. How come?
Jake, we should know this.
Because they got less mass. Air resistance is huge on them, right? And they just sort of die very quickly, right? Okay. When Galileo reportedly dropped the object with different weights from the leaning tower Pisa, the heavier object did get to the ground first. However, the time difference was only a split second rather than the pronounced time difference expected by the followers of Aristotle. They expected it to be 10 times. Same thing in Jake's experiment, right? Now, what are the chances that he... So now he's doing it under the table. You.
I am?
You are.
Why?
I don't know. You tell me why. Okay, it all depends on... Did you actually release them at exactly the same instant?
I don't know.
You don't know, right? I mean, there's likely a slight variation there, so it's hard to say. Sorry. The behavior of falling objects was never really understood until Newton's analysis of second law of motion. Isaac Newton truly changed our way of seeing the world. Flip the page. Okay, now I get to show you something. I need a piece of paper. Yeah, we might have time. And a book. Yeah, big book. Oh yeah, this is good. Perfect. Okay, so what does it say to do? It says, if you drop a sheet of paper and a book side by side, the book will fall faster because of its greater weight relative to the air resistance, right? Like if I do this. Well, Aristotle would say, well, this is maybe, say, 100 pages, 100 times heavier, right? So it should get there 100 times faster than this thing.
It also has a cover on
It also has a cover on it.
Hardcover.
It was close, but the book got there first.
What's the 100?
But it wasn't 100, you're right. I can't believe nobody did that in all those years.
They
Okay,
probably did,
they were just too scared, yeah. Probably burned it stake.
Yeah, there was people
Maybe
like
this guy was just really
this
persuasive.
Exactly.
Maybe he's just really persuasive.
Yeah. So what if I put like the paper on top of the book like that? Will it do that too?
It'll come off of the book.
Will it?
Why?
So like when I did this, right? Like, oops. When I did this, the paper just sort of floats, right? Okay, what's going to happen
Put
here?
it under the book. How about that? Put it under the book.
The paper's gonna fall off because the book's going fast.
Really? Oh, John, are you awake?
The book.
I'm going to drop it on your head now.
That's only so obvious. You have to keep talking. Come on.
Yeah, everyone, all quiet there.
Gee.
Funny how silence makes someone wake up.
Or no, or not.
Say, why does it say
That's
what?
why what's it gonna do?
Give me that. No, you've done that 3 times. It's the 3 strikes and you're out thing.
Mr. Bennett, then
Here,
why?
Louis.
Mr. Bennett.
Here. This is not a battle you're gonna win.
Okay. I'm just gonna put it in my pocket.
No, you're gonna put it here, or I'm gonna walk over there, and I'm gonna make a phone call, and then it's gonna get
You're
worse.
gonna make a phone call.
Uh-oh.
I've given you 2 warnings.
That's because I won't put it on the desk.
Yep.
Wow. I'll put it there.
Okay. I don't need to touch it. I just need it away. I'm pretty sure I gave you fair warning.
Yeah.
If I put the paper under the book, the paper will hold the book up, right?
Yeah.
Like it'll float it, right?
Oh, yeah.
Won't it?
No.
Why not? Float.
I don't know, Miss Bennett. I guess.
There's actually some people that believe that, by the way.
That was very.
People below me always hate it when I do this.
Well, you guys-
Jerome always says, "What are you doing up there?"
Is Mr. Jerome still?
He used to be when I was not.
Boy.
He didn't like that. Okay. I think I have. Yeah. Okay. So you're gonna have to go back. Yeah, I apologize. You're gonna have to go back and finish question 1, right? So get it right this time.
Yeah.
I've circled the correct answer.
Let's do.
Don't say no.
So, Mr. Bennett, why was it that, like, when we were doing that thing with the pulley, like, our mask
Yeah.
fell off of our block? When it
Say no to drugs. No. No, drugs.
There's your... So if a heavy person and a light person open their parachutes together at the same altitude, each wears the same size parachute, who will reach the ground first? Heavy person, light person, same time, or impossible to tell?
Happy person.
I was not gonna be able to put this right now, so I guess.
Didn't we just like talk about how it's gonna be?
Yeah, it's what I've been talking about for like half an hour.
Spreads his wings and flies.
Are you going to sing about it?
Yeah. Spreads his chest.
There must be an answer.
Flies.
Well done. Most of you have been listening.
It's like Stewie.
How come?
overcome their
Yep. The heavy person will reach the ground first. Like a feather, the light person reaches terminal velocity speed sooner, while the heavy person continues to accelerate until a greater terminal speed is reached.
So,
The heavy person moves ahead, and the separation continues to increase as they descend. So they both fall at constant speeds, but the heavy guy, or person I guess I should say, is going faster, so they will actually separate, right?
so you're saying that if me and a fat person were both gonna die, I would last a couple seconds longer than the fat person.
I suppose you could put it in those words.
Right on.
I'm glad that pleases you.
That's right, guys. Big Stewie so bad.
Oh, because I pressed stop, didn't I? Would you stop letting me do that?
Okay, so yes and A.
All right. So now you can get them all right. Right? Now you can get one right.
What more about percent?
You can get one right. Jeez, I gotta stop doing that. You can get one right. You can get two right.
It was no.
Here's question 3. If the force of air resistance is the same for a falling baseball and a falling tennis ball, which will have a greater acceleration?
We're the same. What are those?
The force of air resistance is the same.
What are the same?
Which one's heavier? Doesn't say that.
I could be.
I'm just glad to hear you guys talking about this stuff.
Is without air resistance the baseball football somewhere you have?
No, if there was no air resistance, they'd fall at exactly the same accelerations, right? It's air that causes the trouble.
Oh. Reverse.
Finally, I did it right.
Ah! Shit.
Nate, language. No, just don't. Nate, don't. Really, we're not going to get into that argument either.
But the air resistance, Mr. Bennett, the air resistance is the same.
It's the same.
Don't say the same. It's true, I'll explain. It's true the air resistance may be the same for each, but that doesn't mean the net force is the same, or that the ratio of net force to mass is the same. The heavier baseball has a greater net force per mass, just as the heavier parachute is previously considered. Convince yourself of this by considering the upper limit of air resistance. That is, when air resistance is equal to the weight of the tennis ball. What would be the tennis ball's acceleration? 0. But when the amount of air resistance acts on the heavier baseball, do you see that the baseball still will accelerate?
Yes.
And with more thought, do you see that the baseball has the greater acceleration even when the air resistance is less than the weight of the tennis ball? Tricky stuff. Okay? Well, tricky stuff. You're going to have to sort of ponder that, work through that a little bit in your mind.